Organic chemistry. It's my favorite topic in chemistry. It's the thing I specialize in as a scientist.
Is that going to be in the museum chapter 9?
We'll have some chapter 9 on there, yeah. Does anybody know what organic chemistry focuses on?
Organic stuff.
What does it mean to be organic?
Carbon.
Carbon, right? So organic means it contains carbon. That's the general term. It's not 100% true. You can actually have inorganic carbon in some cases, like a diamond. A diamond wouldn't be considered organic even though it's all carbon. But for the most part, things that contain carbon are organic. Oftentimes the term organic gets thrown around pretty liberally today. So I always laugh when I go into the grocery store and I see the organic fruits. It's like, well, I'd love to see the inorganic fruits. They just big pile of rocks that you grab and take a big chunk out. So
Just the plastic fruit you see in displays.
yeah, even plastic fruit would be considered organic because it contains carbon though, right? It's not made of minerals and rocks and things like that. So if we look at the periodic table, organic chemistry focuses primarily on that top right-hand corner right around carbon. So if we look at what we're made of, what our food's made of, it's almost all carbon, nitrogen, oxygen, phosphorus, sulfur, maybe a little bit of chlorine and iodine and things like that. So organic chemistry is really the chemistry of life. So if we think about what DNA is made of, there's a lot of carbon in it. If we think about what our proteins are made of, a lot of carbon in there. What our fats are made of, a lot of carbon in there. We're not really composed of that middle block of the periodic table. We don't have very much copper in us. We don't have very much silver in us. We don't really even have very much potassium or sodium in us compared to carbon. Carbon's far and away the stuff that makes up life. All right, so let's make a list of compounds or elements that are often in organic compounds. The first one is obviously going to be carbon. We've got oxygen. What are some other ones? Nitrogen. What's another one? Yeah, so iodine, we have a little bit of iodine in us. Yeah, phosphorus is a big one. So if you look at our DNA is held together through a phosphorus backbone. These are the really big four. We also have a little bit of sulfur in us. So some of our amino acid residues have sulfur in them, and they're very important for our proteins. But these are kind of the big 5 elements that compose all of life for the most part. Does anybody remember in the news a few years ago, there was a big hullabaloo about somebody saying that life can actually exist without phosphorus? And they thought that they found a species of bacteria that could live with only arsenic. So if we look at that row, or that column in the periodic table, you see arsenic, that AS right below phosphorus. There was a scientist that thought that they had found a species of bacteria where instead of having phosphorus inside of them, they had only arsenic. Turned out to be slightly incorrect, but there are still scientists out there that say, well, maybe on a different planet, there could be life that lives without phosphorus and instead uses arsenic. Same thing with carbon. Maybe there's silicon-based life out there. So really what we're focusing on when we're looking for life is things containing things similar to carbon or similar to oxygen, especially if we're looking at other planets. All right, so now let's take a look at some hydrocarbons. So what do you think a hydrocarbon is? What was that? It's got hydro in it. What does hydro sound like?
Hydrogen.
Hydrogen, right? And then it's got carbon, so it's something with hydrogen and carbon, right? So why are hydrocarbons a big deal?
Well, they produce them in the possible.
Yeah, so they're important for fats. What's another big thing, especially if we focus on Alberta or parts of the Middle East? Oil, right? So hydrocarbons are what make up oil. They make up fats and things like that. So there's a bunch of different types of hydrocarbons. The first type is called an alkane. And what an alkane is it's a hydrocarbon with carbon-carbon single bonds. So let's take a look at an alkane. And what I want you guys to do is to help me with the Lewis dot structure here. So what I've got is C6H2. Oh. C2H6. There we go. So let's try doing the Lewis dot structure for this alkane. So how many valence electrons does carbon have? 4, right? So we can look at the periodic table. It's in group 4A, which means it has 4 valence electrons. So if we do this, we can say, all right, carbon, we've got 2 of them. Carbon likes to be a backbone, so we're going to put these right next to each other. And then we've got 6 hydrogens. Let me actually do hydrogen in a different color. And so we can start bonding these electron pairs together and say, all right, these are bonds, 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 and these are bonds. So we can redraw this a little bit more clearly. And we can say, all right, carbon has this bond. And then we've got hydrogens around it. So I'm going to draw those bonding pairs just as lines. And now we can see quite clearly that those carbons are singly bonded together. They don't have a double bond or anything like that. What's the shape around each of those carbons? This is some review. So let's ask ourselves how many things are around each of these carbons, whether or not they're bonded atoms or lone pairs. Go 1, 2, 3, 4. So it's got 4 groups around each of these carbons, which means it's going to be tetrahedral, right? Because none of those are lone pairs. So in this case, we can draw it using the 2-dimensional structure, but we know that these are going to be more tetrahedral. All right. So alkanes have this suffix that always ends in -ane. So we have methane. Methane is what heats our homes. We have ethane. We have butane. We have propane. So a lot of these natural gases end in -ane. They have carbon-carbon single bonds within them. So that -ane suffix always indicates that it's a carbon-carbon single bond. All right, now let's go on to the next class of hydrocarbons. And it sounds really similar. An alkene. So if we look up here, it's alkane. This time we've got an ene suffix rather than an ane suffix. And if an alkane is a hydrocarbon with carbon-carbon single bonds, what do you think an alkene is? Yeah, a double bond. So it's a hydrocarbon with carbon-carbon double bonds. Yeah, so if we were to do the analog to ethane that we just did, we could have C2H4, and we could draw out the Lewis dot structure for this. And I'm going to jump ahead to our final Lewis dot structure, but this was one we did on our worksheet. And in this case, you can see quite clearly that the two carbons are bonded together via a double bond, and these always have an ENE suffix. So this would be called ethene. Some people call it ethylene. And then this one would be called ethane. So they sound really, really similar, but in this case, the suffix is the difference here, right? So ethane has an ANE, ethene has that ENE suffix. Does anybody know what ethene or ethylene is used in? Has anybody heard of polyethylene?
Well, it's plastic.
Yeah, it's plastic, right? So we can take these alkenes that are in natural gas sometimes, and we can actually isolate them and then polymerize them into long plastics. And we'll actually talk about plastics a little bit next week. But if you ever see polyethylene, it's just a polymer of ethylene. All right. We've got one last group. Instead of alkenes, we have alkynes. And these have the YNE suffix. And these are hydrocarbons with what sort of bonds in them? Yeah. So they have a carbon, carbon, triple bond. And they normally have a YNE suffix. And so if we think about the analog to ethane and ethene, yeah, it'd be C2H2. And we could draw this using, exactly. So now if we look at the shape around that carbon, it has a bonded carbon and a bonded hydrogen, so it only has two groups around it, which means it's going to be linear. And what's that angle going to be close to? So if we look at the angle, so it's linear, but what angle is that? 180, right? If we go up to ethene, the one above it, what angle would that have? So if we're looking at angles here and here, not quite 90. Well, first of all, what shape do we have with ethene? It's not linear, it's not tetrahedral. We've got three groups around it. It's planar, so trigonal planar, right? And then if these want to be as far away from each other as possible in the three-dimensional space, what angle is there going to be between them? About 120, right? So according to Vesper theory, those atoms and electrons want to be as far apart from one another as possible. So in this case, we've got an angle of 120 degrees. And over here, we've got an angle of 180 degrees. Does anybody remember what the angle was for tetrahedral? If we go back up to our alkane example. It was 109.5. So we can see as we increase our double bonds, those angles get bigger and bigger because we have fewer and fewer groups around them. All right, now let's talk a little bit about some new terminology. A saturated hydrocarbon. What do you think a saturated hydrocarbon means? Yeah, so we could think of it in terms of fats. We have saturated fats and unsaturated fats. What's a saturated fat?
It's like your animal fats.
Yeah, it's that solid fat. It's very, very thick and gooey. It's not typically a liquid fat. So saturated fats are very, very dense. And in this case, you can think of them as being saturated with hydrogen atoms, right? So a saturated hydrocarbon is saturated with hydrogen atoms. And so are these going to be alkanes, alkenes, or alkynes? Alkanes, right? So saturated hydrocarbons are alkanes.
But they have the most hydrogen in carbon.
Exactly. They have the most hydrogen that you can possibly put on a carbon, right? So they have carbon, carbon, single bonds. Conversely, we can have unsaturated hydrocarbons. And so a way of thinking about unsaturated hydrocarbons or unsaturated fats is they don't have all of the hydrogens, right? So in this way you could say that they're not saturated with hydrogen atoms. And so what hydrocarbons would fall in this class?
Like alkyne.
Yeah, alkynes and even alkenes. So anything that's not a single bond would fall into an unsaturated hydrocarbon. Oh. Oh. Alkenes and alkynes. So when we're talking about unsaturated fats, they're fats that actually have double bonds in them, right? So double bonds make fats unsaturated, and it's because they're actually missing some of their hydrogen atoms and therefore form double bonds.
So it's anything that's not a single bond.
Anything that's not a single bond, exactly. Another cool trick you can do is you can think about saturated hydrocarbons in terms of a formula. And they're always going to have carbons and hydrogens, so I'll do C and H. And then what I'll do is I'll label this CN, and then how many hydrogens would we have to have?
Yeah, 3 times N.
Kind of. So what you do is 2N plus 2. So for example, in our example, we had 2 carbons, which would mean we'd have 6 hydrogens, right? If we plug in the 2 for that N, you can actually use this to predict the formula for longer and longer hydrocarbons. They always have this general formula. All right, so now let's take a look at the three-dimensional shapes. Oh. So if we've got an alkane, we said that generally they have angles of 109.5 and that they are tetrahedral. So this is review from our Vesper theory. And then we can have an alkene. These are approximately 120. And these are trigonal planar. Whoops, come back. Come on. Oh. These are 120. And then we've got alkynes. And these are 180 degrees and they're linear. So most of the time, what organic chemists do is when they're talking about hydrocarbons, they will actually draw them out using this way rather than saying C2H2. They like to really show their bonds. And they try to show it using some sort of shape too, so organic chemists love doing dashes and wedges. Yep.
Okay, so for the alkane, I thought it had to be a carbon and carbon atom single bonded. But that just looks like one carbon atom.
That's a good point. Let me actually... Sorry. Let's do it this way.
Awesome.
I'll fix it for you guys. There we go. All right, so we've got 109.5. Typically, you can think of an alkane as anything without double or triple bonds, though.
Why did you have another pointer?
So he just wanted to see the carbon-carbon bond, not the carbon-hydrogen bond. So an alkane is anything consisting of all single bonds. An alkane has carbon-carbon double bonds. An alkyne has carbon-carbon triple bonds. All right, so now let's get into naming conventions. All right, so we'll have two columns, number of carbons, and then the prefix associated with it. All right, so 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons, 7 carbons, 8 carbons, 9, and we'll go on after that. So prefix for 1 carbon, it's not mono like we think it should be. What do we call it if it's 1 carbon with 4 hydrogens? It's a hydrocarbon. It's something we use to heat our house. What was it? Somebody said it. It was methane, right? So with 1 carbon, we always start with the prefix meth. Yeah, which is where the name methamphetamine comes from. It has a methyl group coming off of it. What about 2 carbons? It'd be eth. So ethane, methane, those would be the alkane versions. So if we've got 2 carbons, it'd be ethane. 1 carbon would be methane. 3 carbons? King of the Hill, anyone? Propane. So propane is the 3 carbon analog. 4 carbon, it's in our lighters. Butane. So bute. 5 carbons. Now we're getting into more normal terminology. What do we call something with 5 sides? Pentagon. So we go to pentane. And then what about 6 for Latin roots? What do we call a shape with 6 sides? Hex. So hexane. 7 sides. It's actually heptane. 8 sides. Octane. Oh. So if you go to the gas station and you actually see the octane reading, that's the amount of octane in your fuel. Octane is obviously an alkane, right? It's a clean burning fuel. It's nice and heavy. It works well in car engines. 9 carbons, we've got nonane, or non. And then we can even go all the way to 10, and this is dec. All right, so let's try naming a couple of these molecules here. I'm going to actually show this as a zigzag. A lot of atoms. But anytime we're naming our organic compounds, all you do is count the number of carbons in it, right? So it's 5 carbons. What prefix should it have? Pent. Is it an alkane, an alkene, or an alkyne? Alkane. So what should it be called? Pentane, right? So the key is identifying the suffix for an alkane. It's an alkane with 5 carbons. All right. Let's do this guy. So how many carbons? We've got 3, which should be what? Pro. So pro, and then we've got a double bond in there, which means it's an alkene. So in this case, this would be propene. All right, so we've got an alkene with 3 carbons. Now it looks pretty simple, but there is a slight curveball. Slight curveball. And this curveball is called isomerism or isomers. So let's take butane. I want you guys to draw the structure of butane really quick. How many carbons does butane have? 4, and it's all alkanes, so it's all single carbon-carbon bonds, right? So what I'll do is just draw them like this. So it looks like pentane, but with 1 fewer carbon.
So our carbons are always going to be in the middle like that?
Yep, carbons are always the backbone. They love being in the center of things. All right, so this is one version of butane. But here's the curveball. What if we have the carbons arranged differently? We still have 4 carbons in each of them, right? So if we look at the molecular formula, we've got C4, and then we've got 3, 6, 7, 8, 9, 10. So C4H10. Whoops. What about the one on the right? We still have C4. And we've got 10 hydrogens, right? Oh, I keep on writing 10 instead of H. So what isomers are, is isomers are the same molecule but with a different spatial arrangement, right? It's a compound.
Does that change its properties?
Yes, very much so. So they have, here, let me rewrite this bit. Compounds that have the same molecular formula but different spatial arrangement or different connectivity. So I want to get back to that point of do they have the same properties or not. So what's the main intermolecular force for butane? Would be hydrogen bonding, dipole, ion, dipole. What's going to hold these atoms or these molecules together? Not everybody at once. What's that? We've got non-polar bonds, right?
Right.
Only non-polar bonds in this molecule. How do non-polar molecules stick together? Dispersion forces, right? So in this case, we're looking at dispersion forces. Dispersion forces are affected a lot by surface area to volume, right? In this case, this compound is stretching out and lounging out, right? This one's getting packed into a little itty bitty ball. Which one do you think has more dispersion forces? Yeah, the one on the left has more surface area to volume. So in this case, this one actually has a higher boiling point than this butane. So we can actually separate these based on boiling point and isolate a pure compound by separating them based on their boiling points. So yes, isomers have very, very different physical properties. We also have a unique class of isomerism that I'm not going to test you on, but I just wanted to cover because I think it's interesting. Let's look at our hands. Are our hands the same?
No.
Ish.
Same-ish, right? But if I went to the doctor's office and I said, Doc, I need a hand transplant, give me a new hand, and he gave me a left hand for my right, I probably wouldn't be very happy, right? And so we actually have this thing called stereoisomers, where it has to do with three-dimensional space. Our hands look the same, but you wouldn't want your hand swapped out with a hand that belonged to the opposite hand, right? And this is how drugs work a lot of times, too. It's the same idea as if you had a key to your house, but it was a mirror image of your key. It wouldn't work for opening your door, right? So oftentimes this is a big deal with drug making, is you want to make sure that the drug you make is connected in the perfect shape that you want it to be, because if it's in the wrong shape, it actually will start messing up some other enzymes in your body. So isomerism is a very, very big deal for organic chemists. We want to make sure that they're connected in the exact way we want them to be connected, because otherwise they have very, very different properties. Does that make sense? It's a little bit abstract to think about. Let's do another example, but this time I want to do pentane. Yep. How many carbons are in pentane? 5. So we've got C5H. Let's see, how many would that be? That'd be 5 times, 3 times 2 would be 6. Plus 3 times 2 would be 6. So it'd be C5H12. So if we have pentane, we've got a few isomers that we have to consider. What's the easiest isomer? Yep.
So pentane is compounds that have the same makeup, but
Isomers have the same molecular formula but different connectivity. So pentane has the parent molecular formula of C5H12. So if we try to make a simple pentane, we can just form a long chain, right? Looks like a bat. And then we plug in all of these hydrogens, right? 1, 2, 3, 4, 5. So we've got 5 carbons, right? So I'm going to fill in all of those H's. So we've got 3, 6, 8, 9, 10. Whoops, sorry, this should be 10. Wait, no, 3, 6, 8, 10. I was 12. Sorry, I'm second guessing myself. So this is one example of pentane. And what we call it when it's in a long chain is N-pentane. And what the N stands for is normal, or a straight chain pentane. So in this case, it's pentane without any branching. It's just a long chain of 5 carbon atoms. What are some other isomers we could have?
Like cluster, cluster with pentane. I know we did it.
Yeah, definitely. So let's move one of these methyl groups over. So we could have one where, so that's 3. So we could have one branch coming off of it. So I'm just going to label these CH3s. So do you see how now we don't have a straight chain anymore? We've actually got a branched chain. And so when we number this or try to name it, what we do is we try to number the longest set of carbon chains. So we don't go 1, 2, 3 because we've got a longer chain in there, right? We could actually go 1, 2, 3, 4. So we've got a long parent chain here. And what do we call a 4-carbon chain? What's the prefix for 4 carbons? Not quite, it was bute, right? So butane is a 4-carbon chain. And in this case, we've got a methyl group, that CH3, coming off the 2 position, right here. And so if we were to name this, what we would call this is 2-methyl butane. These both have the exact same molecular formula, but they're very, very different molecules. Yep?
Why is it 2 methyl and there's only one? Because there's 2 methyl.
So you see how we numbered our carbons going along our longest chain? We went 1, 2, 3, 4, because that's our longest carbon chain that's continuous. And then at the 2 position, we've got this methyl group coming off. A methyl group is something containing 1 carbon atom.
Can it just be at the 3 position?
So are you saying why don't we call it 3-methyl butane?
Because you could just number it the other way.
You could number it the other way, but there's actually a set of rules called IUPAC rules, and basically it's trying to make things as simple as possible for the global scientific community, and the rule is this number should be as low as possible. So 2 is smaller than 3, so we preferentially call it that. So do these have the same physical properties?
No,
They're very different, right? Because they have different surface areas associated with them. So we could say that these have very different physical properties. Even though they have the same molecular formula.
So they have different surface areas.
Yeah, exactly. So we can think of this as being, one's way more branched than the other, so it's more compact, it's kind of tighter. The other one's kind of like long spaghetti noodles. It's got very different properties because of that. The same molecular formula. All right. So does that make sense, the difference between isomers? Same molecular formula, just different branching, more or less.
How do you know if something's normal or not?
So normal just means it's a straight chain without branching.
Oh.
So you see how all our carbons are just continuous carbons? We normally put an N in front of molecules that are a straight chain like that. It's a good question. If you go on and take organic chemistry, you'll be swimming in these rules before you know it. So there's a ton of rules. We're just going to kind of scratch the surface of these. All right, there's a couple different types of isomerism that I do want to talk about before we continue on, though. The next one is called cis versus trans isomerism. And these are very important. So let's take an example here. In this example, what we're going to have is 2-butene, and I'll help you guys draw this, but let's start with the suffix here. What does bute mean? 4 carbons, right? So we can start with 4 carbons. All right. And then in this case, we've got the suffix -ene. What does the suffix -ene mean? It's a double bond, right? If it were a triple bond, it'd be YNE. ENE is always going to be a double bond, so we can say, all right, we've got a clue. There's a double bond. Okay, now in this case, where do you think the double bond is based on our naming? Yeah, probably on that second carbon, right? So this 2 carbon basically says if we number this going along our carbons, that double bond's going to start at the 2 and go to the 3.
Why do you go the other direction this time?
It honestly doesn't matter if we're drawing our molecules. You can go left to right or right to left because we're building it as we're going along, right? Okay, so that 2 means that we've got a double bond at that 2 position, which means over here we've got CH3. Over here we've got CH3. And over here we're going to add a hydrogen. And over here we're going to have a hydrogen. So let me move our numbering over. All right, so if we look at the molecular formula here, we've got C4H8, right? So that's our molecular formula. All right, are there any other potential isomers of this? It's kind of a tricky question. So let's draw a different one. So we can go 1, 2, 3, 4. We still have that double bond between that carbon in the 2 and 3 position, right? But what's different here? One CH is down. Okay, so both of these are C4H8. But one thing I'm noticing is if you look at these methyl groups, they're on opposite sides, right? Whereas these methyl groups are on that same face of that double bond. And so we actually have to identify these as being separate. And so what we call these are trans. And basically it means same group on opposite faces. So those methyl groups, one's on one side of the double bond, one's on the other side. And then cis means we've got the same group on the same face. Has anybody heard of trans fats? Yeah, pretty big deal in the news, right? So our bodies are designed to handle double bonds. They're in a lot of the fat that we eat. But let's take a look at what's going on in some of these double bonds. Is it okay if I scroll up? All right. So fats in food. Typically have some sort of structure where I'm going to call this R. R is basically just an ambiguous group. Oh. I'm just going to write H2, H2, H, and H. All right, so if this is a fat in our food, is this a cis or a trans alkene? We know we've got an alkene because we've got the double bond. But is it going to be cis or trans? Do we have the same groups on one face?
Well, like, see the H's, they're on opposite. What are we looking for?
So let's kind of put a line on this double bond and say, are these two hydrogens the same?
Yeah.
Yeah, and they're on the same face of that double bond, so this would count as a cis fat, right? So this would be a cis alkene because these two hydrogens are on the same face, so it'd be cis. And what happens is in some manufactured oils, let me draw this out again. Oh. We get a little bit of these occurring. So if we look at this, we still have an alkene in this oil. But this time, if we look at those hydrogens, see how they're on opposite faces? They're over on opposite sides.
You
So
always look at the double bond.
exactly, you're just looking at what's attached to that double bond. So in this case, the hydrogens are on opposite faces of that double bond, so these would be considered trans fats. So this story behind trans fats goes all the way back to World War II. So in World War II, when we were fighting a global war, there was a big shortage on dairy products, right? Because most of the farmers in Europe obviously weren't raising cattle because they were at war. So there was a big shortage on butter. And so a solution that scientists came up with was they said, all right, what we're going to do is we're going to take vegetable oil and try to convert that oil into an oil that's similar to butter. And when they did that, it was great, and we actually still use a lot of that stuff today, like Crisco. It's hydrogenated vegetable oil, and it was designed to be a substitute for butter in cooking. The problem was we accidentally, in that process, turned a bunch of the fats into trans fats. Naturally, our body can only handle cis fats. As soon as we start throwing in trans fats into our food, our body kind of freaks out a little bit, doesn't know how to metabolize them correctly, and you get a bunch of nasty side effects out of that. So there's been a big push lately to completely eliminate those from foods, even if they're in trace quantities. So now if you go and buy Crisco, usually it'll say trans fat free, and instead of using hydrogenated vegetable oil, they add coconut oil and some other heavier fats into there. So these cis fats are natural fats. And fats. And these are unnatural trans fats.
So all trans fats are like man-made?
For the most part, there are some weird exceptions to that, but far and away, most trans fats that we consume are unnatural. Yeah, so if you ever hear trans fats now, you can say, now I know it's from alkenes. I got this organic chemistry stuff down.